Good. Okay, so we're good? So welcome again to all of you who've been at my lectures in the school, and welcome especially to those of you who have not been at my lectures in the school. And I hope to tell you something about some elementary particles that we understand, but maybe not as well as we should. So today we're going to talk about these two mysterious elementary particles called the top quark and the Higgs boson. The Higgs boson is sometimes known as the God particle, but I'm not sure whether that's a sacrilege here. In any event, it's a name that's catchy in the American media. The relationship of these particles is actually very interesting because it's supposed to be that this Higgs boson is responsible for the masses of all elementary particles. And on the other hand, the top quark is the heaviest known elementary particle. So in principle, the one that is most affected by the Higgs boson. So in principle, we can learn something about how elementary particles get their masses by studying these two states. And well, let's just say the results are ambiguous. So let me tell you a little about that. So in particle physics, we're very proud of our achievements over the past few decades. We have something called the Standard Model, which explains the strong and weak interactions, all of the interactions that are observed to occur at the distances of a nucleus and smaller than a nucleus. And some aspects of this model, though, of course, are still out of reach. And so we're still trying to do scientific investigations to learn about them. And the most important of these concern the two heaviest particles in the theory, namely the top quark and the Higgs boson. I think we understand very well what these particles are, what they do, at least roughly, but we don't understand why they have these properties. And so that's what we're going to explore in this lecture. Now, there's a subtlety in when you discuss the properties of the top quark and the Higgs boson for a colloquium or general audience. And that is that these particles have a lot of unusual properties that we don't understand. But they also have unusual properties that we actually do understand. But in order to understand them, you have to be a physicist. So we'll talk about maybe the second kind first, and then we'll get into the first kind of problem, the thing that's really on the frontier of our understanding. Okay. Let's begin with the Higgs boson. As I said, the Higgs boson is supposed to be the origin of mass for all elementary particles. So this, ordinarily, when you say this to someone who's not a physicist, they say, that doesn't make any sense, because why do you need to give something mass? Stuff has mass. For example, if you look in my closet, you see something like this. And it has mass. So why does it need the Higgs boson? Okay, now, the statement that stuff has mass actually is not correct in fundamental physics. Some stuff can have mass, but other kinds of stuff is forbidden from having mass by the laws of Einstein's relativity. And this is actually a very interesting point, which is, as I say, well understood to physicists, but now I have to explain it to you. If I look at quantum particles, if I look at quantum matter, matter is made of elementary particles. Every particle has an attribute called a spin, which is to say almost all particles are small tops that spin on their axes. And actually in quantum mechanics, the number of spin states, the number of spin directions is quantized. It's not a continuous variation, but there are specific choices. And those choices, it turns out, forbid particles to obtain mass under certain circumstances. So roughly, what has to happen is that particles the massive particles that we see really have two parts, and those parts have to fit together in some way, like these kitchen utensils, in order for the particle to become massive. And that may or may not be forbidden, so let me try and explain that. So let's start with an electron. An electron has a property which is called spin a half, which is the statement that it has exactly two possible spin states. If you think of an electron, a massless electron, of course massless particles move at the speed of light. You can't stop them, you can't slow them down. A massless particle moving at the speed of light can have two spin orientations, which we can call the left-handed orientation and the right-handed orientation. And they're shown in these two figures. If we consider a quantum of light, a photon, then that particle actually has three possible orientations. Left, yeah, that's right, left, right, and intermediate, although this one exists only in principle, actually. In the real world, there are no photons with this orientation, a statement that we'll have to reconsider at a certain stage. Now, in relativistic quantum theory, these two states are completely independent of each other. As long as the particle is massless, you can't turn one of these states into another by jiggling it in some way. But on the other hand, if you want to produce a mass, if you want to produce a mass for that state, then there is actually a problem that you have to confront. So let's look at it this way. Let's say I have a left-handed spinning particle moving not at the speed of light, but at some speed slower than the speed of light. It's spinning in this direction. Now, in Einstein's relativity, when anything is spinning, moving slower than the speed of light, you can run fast enough to catch up to it. And eventually you find it in a state like this, where it's at rest, of course spinning in the same direction. And then if you run even faster, you find it going the other way with respect to you as an observer, and still spinning in the same direction. Now, please look, it's a right-handed particle. So whereas a left-handed spinning thing and a right-handed spinning thing were totally independent when they were massless, when they're massive, by doing the transformations of relativity, you can turn one into another. In order to make a massive particle, then, these two states have to have the same quantum numbers so they can mix together in the way symbolized by those kitchen utensils that I showed you on the previous slide. Now, is it possible or not? Well, ordinarily you would say, what's the problem with that? But it turns out that as we understand more about particle physics, we've discovered that there's a barrier to this transformation. That actually, when you look at the fundamental interactions, this standard model that I talked about, these two states of the electron actually have different quantum numbers and are forbidden from combining with each other. And that's part of a longer story that maybe I don't have time to tell you, but let me tell you a few things about it. First of all, I'd like to tell you that the model that predicts this is an extremely well understood model. It contains particles which mediate radioactive decay, called the W, and the W has a neutral partner called the Z boson. W and Z are very heavy particles. They weigh about 80 and 90 times the mass of the proton, respectively. And they took a long time to discover, although people had glimpses of them as early as the late 1950s. In the 90s, we were able to actually do accelerator experiments that produce Z's in the laboratory by colliding electrons, matter, and their antiparticles. So you bring together matter and antimatter. If you bring them together just at the right energy, the energy mc squared of the Z boson, you make a Z boson. And then one can study this Z boson in great detail. So this is what I explained to these students in a previous lecture. This is a very interesting curve. This is the resonance curve of the Z boson. So if you bring together the particle and antiparticle just exactly at this energy, it very easily makes a Z boson. And then as you go away from that energy, there's a definite shape with which the rate of production of Z's rises and falls. And what's amazing about this is the concord between theory and experiment. So the little red dots are actually experimental measurements of this rate done by an experiment called OPAL that lived in a large accelerator at CERN, the laboratory in Geneva. The black curve is a one-parameter fit, where the parameter is the position of the resonance. And you can see that there's fantastic agreement between those, the theory and the experiment. Both are very non-trivial. I mean, it's really, in each case, 100 man-years to develop each side of that. The theory actually includes all of the fundamental interactions. It includes, of course, the weak interaction, because this is the carrier of the weak interaction. It includes the strong interaction because some of the properties of the Z boson have to do with its interaction with the quarks, and they actually contribute to the width of this curve in a significant way. And it has to do with electromagnetism, because electromagnetism is the effect that makes this curve, as you see, slightly asymmetric. It's slightly bent over to the high side. And that's an effect of quantum electrodynamics, which one had to compute very accurately. Now, among the things we've learned by doing these experiments is that there is a definite asymmetry between the left spinning particles and the right spinning particles. This curve gives one illustration of it. It involves a partner of the electron called the tau lepton, which can decay to a pi meson, a quantum of the strong interactions and the neutrino. It turns out that you can analyze the spin of the tau lepton by looking at the decay, and in particular the energy of the pion. And if you know some particle physics, you can figure out that a left-handed spinning tau produces a slow pion, and a right-handed spinning tau produces a fast pion. If you look at the data, what you see is that there are more slow pions than fast pions. So that means that somehow the Z particle couples more strongly to the left-handed tau than the right-handed tau. And there are other experiments that show that with the same ratio, the Z couples more strongly to the left-handed electron than the right-handed electron. But the Z couples to a charge, which in our theory is as fundamental as electric charge. So the left and right can't be put together unless something else happens. Okay. Well, as I said, there is a grand theory that includes all of these things. It was developed by these people, Sheldon Glashow, Abdus Salam, and Steven Weinberg. They're looking very smug in this picture because they are about to receive the Nobel Prize for creating this theory. Mr. Salam, unfortunately, is no longer with us, but whenever I meet Glashow or Weinberg, they're still looking very smug, because after now 30 years, we haven't been able to tear apart this theory and destroy it. Actually, it works better than ever as we do more and more experiments. Now, if the left-handed and right-handed electron have different quantum numbers, how can we put them together to make a massive particle? Well, it turns out that we need an agent which has some asymmetry in it that couples to both halves and can combine them. And this agent is called the Higgs boson, or the Higgs field. The Higgs field acquires a value. It fills space, essentially. So it's a non-zero field present everywhere in space. And when the Higgs field is there, it can change a left-handed electron into a right-handed electron. And the asymmetry comes because the value of the Higgs field could be plus or minus, or actually some other values as well. But it spontaneously chooses a certain value which is asymmetric with respect to the charge that is differentially carried by the left and right-handed electron. So we would view that as a kind of potential energy for which the symmetric point is here, but the minimum of the potential energy is at an asymmetrical point. Actually, there's a whole manifold of these asymmetrical points, but the universe, or the Higgs field in the universe, chooses one, and it sits down, let's say, pointing that way, in an asymmetrical configuration. And by virtue of that, it can make the flip of quantum numbers necessary to make the electron, the quarks, other things massive. And maybe I should also say, particles with larger masses have larger masses because they have a larger coupling to this Higgs field. Now, the idea of a field spontaneously breaking a symmetry, that is, it has a symmetrical equation of motion, but an asymmetrical configuration, this is nothing new. It happens macroscopically when you line up a pencil, for example, and you let it fall into a random direction. But it also happens with many degrees of freedom interlocked in specific systems that we meet in physics. An example is a magnet. In a magnet, we have a very large number, 10 to the 23rd, of iron atoms. Each one has a spin, which comes from the electron spin, which I just described. At high temperature, the magnet is oriented randomly. At low temperature, these spins line up. And they don't know which direction they're going to align in, but at least they like to be all pointed in the same direction. So that magnetization is an example of the kind of spontaneous symmetry breaking that we need from the Higgs field. Another example is a superconductor. I don't know how many of you have seen a demonstration that when you cool down, for example, aluminum to a few degrees above absolute zero, it begins to eject magnetic fields. And if you put a current through it, the current would actually flow frictionlessly without resistance. This is a picture of a demonstration. This is a magnet down here. Sorry, that's a magnet. This is a superconductor. And the superconductor repels the magnetic field of the magnet, and actually enough to actually levitate the magnet. Now, what happens in superconductivity and magnetism and many other systems is something that you can draw like this. If you look at the energy versus the momentum of a zero-mass particle, it turns out that they're exactly proportional. So the particles move at the speed of light, and a consequence of that is that their energy is equal to the speed of light times the momentum. And if I make the momentum zero, the energy goes to zero, which is to say there's no mass. But for a massive particle, when you make the momentum go to zero, what's left is some finite energy, and that's the E equals mc squared, the energy at rest of a particle according to Einstein. Now, what happens when you break a symmetry is you have two branches like that. Actually, this would be for electrons and anti-electrons. They mix at this point, and they open up an energy gap like that. There are many systems in solid-state physics. Superconductivity works like this. And now we understand that elementary particle physics also works like this. When the Higgs field turns on, it opens a gap like that so that the particles that couple to the Higgs field have a finite energy above zero, and these negative energy states are representing antiparticles. Okay. Now, we know what the Higgs field does. We know that it influences quarks, leptons, W and Z bosons in exactly the way that the theory predicts. The thing that we don't know is we don't know actually what it is or why it does what it does. And that's actually one of the big mysteries of physics. We give this field a name, the Higgs field, but it doesn't make it less mysterious. Now, despite the fact that the Higgs field is mysterious, or maybe because it's mysterious, you can go look for it. Now, it's hard to look for something which is quiescent and filling all of space. But in quantum mechanics, if you shake anything, the excitations are quantized. They're, again, elementary particles. And we can go look for those elementary particles. And so the elementary particles that occur when you wiggle the Higgs field are called Higgs bosons. And one can go look for them in accelerator experiments. Now, it turns out that the Higgs boson is short-lived if you produce it, but it decays to some definite things. And I explained to these students this morning that the Higgs can decay to 2 gamma rays, or it can decay to 4 so-called leptons, 2 electrons and 2 muons, or 4 muons, something like that. And well, if you collide together protons at a sufficiently high energy, you can actually produce these events, and you can look for decays that look like that. Well, you need quite a high energy. In fact, the energy that's required is the energy of this machine called the Large Hadron Collider in CERN in Geneva, Switzerland. It's an array of magnets 27 kilometers around, so it's really a macroscopic accelerator device. It circulates protons in opposite directions. They collide with one another, and they try to produce the Higgs boson and various other kinds of reactions. Let's look at a few scenes from that. First of all, when you collide elementary particles, of course, it's very difficult to visualize what's happening in the event. So you need a special purpose detector in order to detect the fast energetic particles that come out, eventually to take a picture of the event. In the Large Hadron Collider, the energies are the largest ones ever created by humans. And so the imaging of these events is also very subtle. And because when a particle is very energetic and moving relativistically, it's just hard to slow it down, they have to be enormous. And so this is a design of the ATLAS experiment, one of the 2 experiments whose results I'll talk about. You notice that, so what happens is a proton beam comes in like this, another proton beam comes in from this side. The beams are very carefully timed, so they collide right in the center. In the center, there's a device that tracks the charged particles. Outside of that, there's a magnet which bends the charged particles. Outside of that, there's a device called an electromagnetic calorimeter that visualizes the gamma rays that come out of the reaction. Outside of that, there's something called a hadron calorimeter, which visualizes other kinds of strongly interacting particles. And finally, anything that gets out of that, so from here to here, it's basically 5 meters of stuff. Anything that penetrates that is probably a particle called the muon. The muons are the main constituents of cosmic rays. And then one can track muons in this very interesting device on the outside. The whole thing is about 6 stories high. These are people, just for scale. I heard an ATLAS experimenter say, when we do the experiment, we ask these people to get out of the way. Okay, just to get an idea of the scale, have a look at this thing here, which is a superconducting magnet that bends the muons. Here's a picture of that thing being delivered at CERN. So this monstrous thing is this tiny piece of the ATLAS detector. You get the idea. On the other side of the LHC, there's a detector like this. It's called the Compact Solenoidal Detector, or CMS. It's called compact because it's much smaller than the ATLAS detector. It's only 4 stories high. It's composed of rings of magnets, and then the various particle imaging stuff in the center. Again, these are people to get the scale. And here's a photograph of those rings of magnets being installed at CERN. And these are the people doing the installation. So you can get an idea, again, of the monstrous size of these experiments. Here is an event picture taken by ATLAS. So what happens here is that 2 protons come together. A quark from one proton hits a quark from another proton. They then go off at some angle, and as quarks rip through the vacuum of space, well, rip through space, not interacting with anything, but just basically pulling themselves apart from one another, they create lots of pi mesons, k mesons, protons, all of these strongly interacting particles. And then the tracks of those particles are visualized by the detector. And these green things represent the energy deposited when those particles smash into the thing that I called the calorimeter. So you see the two quarks coming out of this interaction region, moving back to back. And when they measured the energy, it turns out that the two quarks together have an energy which is half the original energy of the protons that went in. So this number, 7 TeV, is 7,000 times the rest mass of a proton. And that energy is being liberated in various processes, some of which are more interesting than others, but some of them are very interesting. Now, the kind of process that I told you to look for was a process where you make a Higgs boson and it decays to 2 gamma rays. And a gamma ray would be seen as something that has no track, and then it has a deposition in the electromagnetic calorimeter, the thing which is supposed to measure the energy of gamma rays. And so it's an event that looks like this. Of course, when the protons smash into each other, lots of other stuff comes out, and that's what you see here. But you see there's no energetic track that points from here to here, or from here to here, and here you see a large energy deposition in this ring of CMS that contains the electromagnetic calorimeter. So that's what a Higgs boson being created and decaying to 2 gamma rays looks like. Now, as I told you, these decays are very rare. First of all, the Higgs boson production is rare, and then only a part in 1,000 of the time does the Higgs decay in this way. And so eventually you have to keep taking the event pictures and pile them up, and actually you have to go through 2 trillion such event pictures to find one event like this. Hopefully you can get a computer to do it, because it takes a lot of time for graduate students to scan 2 trillion pictures. And when you do that, what you find is a distribution like this. So now what I'm going to do is to measure the energy and momentum of these gamma rays, add them together. That gives me the mass of the parent. What I see is a smooth distribution that comes from other kinds of strong interaction processes. And on top of that, there's a signal at a definite place, 125 in these units of GeV. That is roughly 130 times the mass of the proton. And that, one would say, is the signal of a new elementary particle, the Higgs boson. There's another kind of reaction I told you to look for, which is one in which the Higgs boson decays to muons and electrons. So here's an example of that. The Higgs decays to 2 Z bosons, which in turn turn into 2 muons and 2 electrons. Here's a picture from Atlas, and you can see it. The muons, remember, are the things that go all the way through the detector. And so here you see the track of one muon, and here the track of another muon. The electrons, this is a better view to see the electrons, have a track which ends at the electromagnetic calorimeter and has some electromagnetic energy deposition. And so in all, 2 muons and 2 electrons, which you can see here and here, but better here and here. You measure their momentum vectors, you add it up, you compute the mass of the parent. It turns out to be just where the other resonance was, about 125 GeV. And if you look at the whole sample, it turns out that there are only about 20 events observed originally by the Atlas experiment, but it's very clearly a signal above the computed backgrounds. So again, really evidence for a new kind of particle that was being produced in the Large Hadron Collider experiments. Now, as I said, we've now been able to see the Higgs boson in many other decay modes. It's supposed to decay to so-called bottom quarks, to these tau leptons that I told you about, to the W boson, which mediates radioactivity, in addition to the decays to Z and gamma that we've already discussed. These are the measured values relative to the prediction of this standard model of particle physics. So roughly 0 here is no Higgs boson. 1 is exactly what Glashow, Weinberg, and Salam would have expected. 2 is twice as many. There's still, statistical error on these points, but you can see that that theory seems to actually explain pretty well how many Higgs bosons are produced and how they decay at the LHC.
Can I ask a question?
Please.
The fact that most of them are actually to the right of the line, does that mean anything? Should we start interpreting that? I understand that individual data points are certainly within 1 sigma.
Yes.
But they're systematically to the right.
We don't know, actually. I think if you add it all up, it is not a significant, the average is not a significant deviation from 1. But nevertheless, you could begin to wonder. If it's not exactly 1 when we have very high statistics, that would indicate that there's something wrong with the standard model. But I think no one is claiming that yet. But good observation. Okay. Now, the mysteries of the Higgs boson are linked to mysteries about other elementary particles. And so, in particular, one of the very important things is the mass of elementary particles. So there are 2 kinds of matter-type elementary particles. They're called leptons and quarks. The leptons are the electron, the muon, the tau, which we talked about, and the neutrinos, these mysterious, chargeless, very fast-moving particles that appear in nature. The quarks are the building blocks of atomic nuclei. 2 U-type quarks and a D quark make a proton. 2 D-type quarks and a U quark make a neutron. There are other kinds of quarks, which I've listed on this slide, called S, B, C, and T. We don't know why they exist. As far as life is concerned, all we need is U and D. But nevertheless, they're there, and we should have an understanding of nature that includes them. Now, something odd is that the masses of these particles are all over the map. So I've written things here in units of GeV. A GeV is about the mass of a proton. And you see that the numbers are very different. The electron is half of 1,000th of a GeV. The heaviest known quark, the top quark, weighs 173 GeV. And the other particles span the whole range in between. And let me just emphasize, we have no knowledge of how to predict these numbers or understand them. We observe them. And where they come from is a mystery. And in particular, why the lightest quark is 100,000 times lighter than the heaviest quark is something that we absolutely do not understand. Now, I could tell you that in the standard model, the ratio of these 2 masses is equal to the ratio of the couplings of those particles to the Higgs field. So ultimately, the Higgs field knows why the up quark is less massive than the top quark, or vice versa. But you've got to admit that this is not a very good explanation. It just kind of pushes it back in 1 step into a mystery that we still don't understand. Now, there's one more very important thing that we don't understand, which is anomalous. Is it that the up quark is light, or is it that the top quark is heavy? And it's not a silly question. It's really an existential question, because we'd like to know where the top quark comes from, why it exists. It is a very heavy particle. It actually is unstable. Its lifetime is something like 10 to the minus 24 seconds. So you make it, poof, it's gone. We don't know what role it plays in life, in biology. Presumably it has none. But there's some reason why it exists in the universe. And to understand that question, we'd like to understand whether it's important that the top quark is as heavy as it is, or whether that's just an accident. So let's talk a lot more about that. So here I put actually some questions which are really related to this. Is the top quark a special quark whose large coupling is somehow connected to the story of what the Higgs boson does, and connected to the mechanism of this spontaneous symmetry breaking that I talked about? Or is the top quark a perfectly ordinary quark whose coupling to the Higgs field is of ordinary size, while the couplings of all the other quarks and leptons are highly suppressed? And this is obviously a dichotomy. If you believe in this, you would make one kind of fundamental theory. If you believe in this, you would make another kind of fundamental theory. And people go off in both directions, and so far they haven't met yet, or actually even succeeded, so what can I say? Okay, now the Standard Model allows us to express the strength of the coupling to the Higgs field in some units. And actually, it's interesting to write down the strength of all of the fundamental interactions in a numerical way. So let me just throw these numbers at you. So ordinarily, you think of electromagnetism as some kind of, well, maybe not the strongest interaction in the world, but something that we can definitely feel with electric fields. Actually, the strength of electromagnetism is described by a dimensionless number, which is the electron charge divided by 4 pi. And also, there are factor h bar c, the quantum and the speed of light, to make it dimensionless. And rather famously, that number is 137. Actually, 137 is a kind of mystical number. One of the really great astronomers of the early 20th century, Sir Arthur Eddington, actually went insane trying to explain the number 1 over 137. But it turns out, when you understand quantum field theory better, you find out that that's not a fundamental quantity. 137 is the result of the physical electron at large distances. If you go, as it were, inside the electron and peel off some levels of structure, it turns out that the strength of electromagnetism gets stronger. And for the weak interactions, the real strength is about 1 over 128. So it was actually fruitless to try and explain this number. And this is probably the number to which you should compare the other elementary forces. The W boson couples with a strength of 1 over 30. So actually, the weak interaction is actually considerably stronger than electromagnetism. The strong interaction, this is the strength of the coupling of the thing called the gluon that glues quarks together in the proton, is 1 over 9. So it's actually weak. It's not much stronger than the weak interaction. And on this scale, the strength of the coupling of the top quark to the Higgs boson is about 1 over 13. So it's a number that doesn't seem so different from the other numbers in this plot. And maybe that's some evidence that the top quark is a perfectly ordinary object that doesn't do anything special. The strength of the coupling of the Higgs boson to the bottom quark, the next heaviest quark, is 1 over 42,000. So maybe this is the funny number that we would have to explain. Okay. Now, the top Higgs coupling is large enough to create a surprising effect in top quark decay. Actually, the top quark is unstable, and actually, since it's so heavy, it can decay to a W boson just outright and a bottom quark. Now, most quarks decay through the weak interaction. That's radioactive decay. For example, ordinary beta decay is a down quark turning into an up quark and giving rise to an electron and an antineutrino. And the way that works is the down quark emits a W boson as a quantum fluctuation. But it doesn't have enough energy to make a whole W boson. It just exists as a quantum blip for a very short period of time, and then that W boson turns into the electron and the neutrino. But the top quark is so heavy that the decay can produce a real W boson, which subsequently decays either to a lepton or a pair of quarks. And actually, you can look for these W's in top decay, and let me show you a few pictures of that. Here's one of the first top quark events discovered at the Tevatron accelerator at Fermilab. Here is maybe the side picture of the reaction, and it kind of gives you an idea of what's going on. You see here, the decay is the top quark produces. So the idea is that one top quark will decay to a bottom quark and a W that decays to a quark and an antiquark. Each quark produces what we call a jet, a little bundle of pions, kaons, and other strongly interacting particles. So in the end, there are 4 jets in the reaction, the electron and a neutrino, which is unobservable. Here's the electron. You see 1, 2, 3, 4 jets. Actually, if you go really close in to the below a centimeter scale around the vertex, you see that 2 of the jets have a particle that somehow started here, went to here, and then decayed. And that is the so-called B meson that contains the B quark. So what we see is the top quark decaying to a B quark, which is identified by this flight path of a meson, plus some jets, and the other one decays to a B quark, the electron, and the unobserved neutrino. Here's some top quark pictures from the LHC. Here you see the same pattern. An electron, a 3-jet system here, and a B-tag jet coming down. If you unroll it and you look at the energy deposition, you can see, for example, on the hadronic side, there are 3 little patches of energy deposition representing the 3 jets. That's a blow-up of it. Let me just go past that. Here's a beautiful picture from the CMS experiment, where you see very clearly on each side 3 jets as the result of the top quark decay. And here, this is a somewhat complicated picture, but in this visualization from Atlas, each cone is a jet. The red thing there is a muon, and the dotted line here is the inferred direction of the neutrino, which went along with the muon. Now, when you get a sample of these things, you can actually do a kinematic reconstruction of the event. So you can actually figure out the angles between all of these tracks. And you can also boost. For example, you can view this event not in the lab, but in the rest frame of the top quark. So you can analyze very carefully how it decays. Oh, by the way, if you add up the energies of the jets, you get a pattern like this. So that's how we know that the top quark mass is 173 GeV. It's this big peak here. And if you take a pair of jets, it turns out that their distribution peaks exactly at the mass of the W boson. So we really can look at the kinematics of these events and understand perfectly well that it's a top quark decaying to a W and a jet, and the whole thing has a mass of 173 GeV. Okay. Now, since we can reconstruct the W bosons, we can also measure the properties of the W boson. And let me remind you again that a spin 1 particle has these 3 polarization states, the left spinning, the right spinning, and the intermediate one. And we can ask what fraction of these are made in top decay. And this turns out to be an interesting question for the following reason. If you have a massless particle like a photon, I told you that only these 2 states, the left and right spinning ones, exist in nature. If you take Maxwell's equations, which are supposed to explain electromagnetism, and you solve Maxwell's equations, you find this solution and this solution, but not the other solution. This one is there only if the W is massive, and actually only by virtue of the W's interaction with the Higgs field. And this is something that you can understand through the analogy with superconductivity that I talked about before. Basically, the left-handed and right-handed spinning states contain electric and magnetic fields that spin, literally rotate around the direction of the W as it goes through space. The intermediate state is some electric field that bobs up and down. And this is actually a motion not of the W itself, but of the medium that's making the W massive. So this is actually an element, a state that comes from the Higgs field rather than from the fundamental W field. Now, what is that? Can we visualize that experimentally? Well, it turns out that it's quite interesting that the top quark has this ordinary coupling to W's, but it has a strong coupling, as I've told you already, to the Higgs field. And so what you would expect is that when the top decays, it's much more likely to go into this state than into either of these states. And experimentally, that actually turns out to be true. You can measure the fraction of that zero state, and it turns out that when you analyze that fraction, it's 70% of the top decays go into the state which wouldn't even exist if the top quark weren't, if the W boson weren't massive. And one can explain that actually by saying that to produce that state, it goes with the quantity alpha T, the strength of the Higgs coupling to the top quark. For the WL, it goes with the ordinary weak interaction strength. The ratio is 2.3 from the numbers I gave you before. And that predicts, and it's actually correct, that 70% of the top quark decays are to this W0. And as I say, if you go and measure the angles in W decays, here's a very beautiful measurement of that angular distribution from the LHC. The prediction of 70% is that red curve, and you see that the data falls right on top of it. So this is a weird thing about top quarks and Higgs bosons, but it's something we actually understand. So now we need to go to the things that we don't understand. So, as I said before, we know that the Higgs boson exists. We know that it is the quantum of this field that stretches through space. We know that that field can create the left-right flip, which is responsible for giving masses to all the leptons and quarks, and also, of course, the W and Z bosons themselves. We don't know, though, what that field is made of or why it fills space. Why is that energetically favorable rather than just having a zero value everywhere, which you think would be much more sensible? So what causes this? Well, this is something that I think physicists spend their nights staying up and worrying about this. I'm certainly one of those people. And now we have to ask why it occurs. In the standard model, there's no explanation. The standard model just says, that's the potential, live with it, that's all I can say. So now what we have to do is to look for some kind of more fundamental explanation. In superconductivity, there is a more fundamental explanation of why that particular symmetry breaking occurs. It turns out it's a very delicate phenomenon. When you cool a metal down to very low temperature, electrons are actually bound. They pair up. And those pairs of electrons then have changed their, if you like, what's called their quantum statistics. Instead of obeying the Pauli exclusion principle and repelling each other as individual electrons do, the pairs of electrons obey a different kind of statistics called Bose-Einstein statistics, and they like to clump together. And so once you've made the pairs, you have something that can actually, as it were, condense and form a fluid of electron pairs inside the metal. So now the question is, can we find an explanation like that for symmetry breaking in the weak interactions? So let's see. First of all, I guess I'd like to give you an explanation which actually doesn't work, but it almost works, for why the electroweak symmetry is broken, which has to do with the relation between the Higgs boson and the top quark. And that goes back to the picture that I showed you before of the the energy states of a particle which is massive, which involves particles and antiparticles. So it turns out that a massive fermion, like the electron or the top quark, is described by an equation called the Dirac equation. And the energy states of the Dirac equation are laid out something like this. There's the energy gap that I told you about. There's a set of energy states that begins at mc squared of the electron. And there's a set of energy states that comes to minus mc squared, and then it goes down to minus infinity. And electrons and top quarks obey the Pauli exclusion principle. So you can put one particle in each quantum state. And so to get the minimum energy, you would fill all of the negative energy states, and you would leave open all of the positive energy states. Now you can think about excitations. For example, if I put an electron here, that's a physical electron. But there's something else I could do, which is to take an electron out of this level and move it up to there. Then I have a physical electron here, but here I have what we might call a hole. A hole is the absence of an electron charge, which is to say it's an extra positive charge. And when the hole moves around, it moves around like a particle with the same mass as the electron, except it has a positive charge. If I bring together a hole and an electron, the electron can fall into the hole, and the electron and whatever that was annihilated. So this is antimatter. That hole is the antiparticle of the electron. We call it a positron. We can do the same thing with top quarks. Of course, for the electron, this is a very small energy, 1/2 of a 1,000th of a GeV. For the top quark, this gap is 170 GeV, so we need to have a lot more energy to bridge from here to here. But now let's think about what would happen if the Higgs boson, the Higgs field, didn't exist, and then we turn it on. If there were no Higgs field, the top quark, like the electron, would have two pieces, the left and right piece, and they would be forbidden from coming together. So the spectrum of top quark states would look like this. The top quark would be massless. The negative energy states would be filled. The positive energy states would be empty. Now turn on the Higgs field. If we do that, that will open a gap. And it will raise the energy of these states, and it will lower the energy of these states. And that will decrease the energy of space. So this is energetically favorable. And so you can see from this argument that if I couple the Higgs field strongly to the top quark, the symmetric configuration, that is this one, is actually unstable. It goes over to a configuration where the Higgs gets an expectation value, fills space, lowers the energy of all the top quark states, and then proceeds to break the symmetry that we need for the theory of the weak interactions. There's only one problem with this, which is that it doesn't stop. The Higgs field, if you really take this model seriously, just gets an infinite value. All these states drop down to minus infinity. These states go up to plus infinity, and the situation is completely unstable. So one of the big problems then is, if you take this seriously, how do you make this evolution stop and find a stable minimum in which the Higgs field rests? So to make sense of this calculation that I just did for you in a pictorial way, we need to figure out some way in which we can give some more structure to the Higgs field, so we can give it a context in which we can actually calculate a potential that goes down and comes back up again. And there are various ways of doing that. And I'd like to just quickly go through a few of them and talk about the experimental tests of those ways. Which way is the right one is still a mystery. And as I say, with my colleagues, we still fight about this every day, and we don't come to any conclusion. And also the experiments are very inconclusive, as we'll see. So the first thing you can do is say that the mechanism of symmetry breaking in the weak interactions is just the same as in superconductivity. The Higgs field is made of some more elementary particles. They form pairs. The pairs condense. Instead of condensing and forming a fluid in a metal, they form a fluid in all of space. And that idea was proposed in the late 1970s. It's called Technicolor. It's a very attractive theory. As I've told these people in the lectures, it has lots of really beautiful properties in terms of explaining aspects of the weak interaction that we wouldn't otherwise understand. Unfortunately, we now know that this beautiful theory is completely wrong. And probably the most important reason for that is that in this theory, there is no light Higgs boson. The Higgs boson would weigh, instead of 100 GeV, it would weigh 1,000 GeV. And it would not be apparent as a resonance in the way that I showed you it really is in nature. So this is a nice idea. Just copy superconductivity, but it doesn't work. Throw it away. The next idea is that the Higgs is an elementary scalar field, but there's some symmetry that keeps it from getting a mass, so it has an absolutely flat potential. And then we turn on its coupling to the top quark, and that makes the potential curve in some way. And with sufficient control over the theory, you can actually compute that. There are such symmetries that you could invoke. One of the nice ones is called supersymmetry. Unfortunately, I don't really have time to give you a full explanation of what supersymmetry is. But let's just say that for every fermion, there's also a field which is related to that fermion. For each quark and lepton, there's a new field related to that. For every vector boson, like the photon, the W, and the Z, there's a new kind of matter field associated with that. And the interplay between the particles we know about and these new particles is such as to generate a Higgs potential which is absolutely flat. And then when we introduce the coupling to the top quark, something interesting happens. So what happens is that there are interactions between the new top quark fields and the Higgs boson. And those interactions, actually, you can compute the change in the potential of the Higgs field that comes from this process represented diagrammatically here. It turns out that it does the right thing. It bends the potential down, forms an asymmetrical minimum, and that minimum turns out to be stable. So this is a beautiful theory for making the form of the Higgs potential that we need for the strong interactions. Actually, there's a part of this which is really quite interesting and very lovely. And that is that because we've turned the top quark into a field like the Higgs field, there are actually three fields in play which compete with each other. There's the field associated with the left-handed top quark, the field associated with the right-handed top quark, and the field associated with the Higgs boson. And those have a kind of competition. So in principle, any of them could have a potential that bends down, and any of them can get this vacuum expectation value that fills space. So that competition you can express in equations, and here are some, well, pretty complicated equations that express that. Essentially, what happens is that the masses of each of these fields start from some value at very short distances, let's say at a very fundamental scale, like the Planck scale, or a scale of grand unification. Then they get changed by these equations as we go to larger and larger distances, and eventually they start becoming negative. And the first one that becomes negative, that's the instability toward symmetry breaking. And if you look at the coefficients, it turns out that there's a coefficient 1 here, 2 here, and 3 here. So this field, which is the mass of the Higgs boson, is the first one that becomes negative and starts the instability. It's a non-trivial calculation. and it comes out in the right way to give you a good phenomenology for the weak interactions. So it's a very beautiful property of this explanation for the Higgs field. Now, the only problem with this is that these other fields associated with the top quark have to exist. And they also have particles, which would be the analogs of the Higgs boson, except they'd be top-like. And actually, to make this mechanism work, the masses of those particles have to be not very far from the scale of the Higgs potential, that is a few hundred GeV. So we can go to the LHC and look for those particles. And actually, a lot of work has been done looking for particles like that. So for example, one can look for this reaction where the top, it's called the top squark, decays to a top quark and a partner of the photon, and then this will decay to WB, and then you sort through your pile of events to look for final states that look like that. And here are some plots from a paper that did that. Unfortunately, there are lots of other rather complicated processes that produce the same final state. For example, ordinary top decay accompanied by, let's say, a Z boson that decays to neutrinos will produce this signature. And so the colored boxes represent all the various kinds of perfectly complicated but perfectly well understood reactions. And when you add them all up, the data agrees with that sum. So there's no room here for the top quark. And this actually is the current situation in terms of the searches for the top squark. This is now 1,000 GeV. I told you that squark would have to be in this range of a few hundred GeV. This is the particle that it decays to, the partner under supersymmetry of the photon. That usually is thought not to be so high, although it could be up here somewhere. But this range of those two masses is actually excluded by the searches at the LHC. So ordinarily, for the mechanism I told you, you'd like to be living in this region. And unfortunately, people looked, it's not there. Maybe you could go to some other regions of the space, but we're still looking very hard for those particles. Now, another thing that we could try to do is to think about the Higgs boson as another kind of composite particle. Maybe not the thing that directly condenses, but another kind of particle called a Goldstone boson. And there's a class of theories that use this idea. You make composite particles that don't condense, then you couple them to the top quark, and that generates, in a similar way to what I described in supersymmetry, a small potential that bends down and creates an asymmetric vacuum. And one type of model there is called the little Higgs model. And in that model, actually, again, things work very beautifully. You introduce some top quark multiplets. You also have to include some massive partners of the top quark, which I call capital T. This is the diagram that represents the effect that I showed you pictorially, which generates a negative bending down of the potential, but then it doesn't stop. But then it turns out that if you include, in particular, this diagram, which includes the capital T, that causes the potential to bend up again, and it gives you a very beautiful and consistent minimum. And this is some technical term, but in fact, this theory does work to produce a Higgs potential of the right kind. And here's the formula. Please excuse me for burdening you with a formula. But the important part of it is that it has a negative sign in front of it. So it means the potential does bend down correctly. Ultimately, that negative sign is the same instability that we saw in the pictorial argument. But now it's controlled by adding this additional structure. The mechanism is beautiful, but to make it work, the heavy partners of the top quark must exist. And so again, we go to the LHC and see if we can find them. So here is a typical slide from a paper that looks for these things. Once again, what you're looking for is the capital T decaying to WB. So you're looking for something like top quark production, but with much larger mass. Maybe it would be over here somewhere. And here's the data, and you see that there's no evidence for anything that's being produced with that large mass. So people have done this kind of study also very systematically. So you can think of the top partners, they could decay to WB, they could decay to Z and top, or they could decay to Higgs and top. And if you think about that, you can draw everything in a triangle where you don't have to know what the various probabilities are of these three decays. You just know that they add up to 1. So this is the probability that the top quark, let me just get that correct with this, decays to WB. This is the probability that that quark will decay to a Higgs boson and a top quark. And then to the extent that these two probabilities don't add up to 1, the third probability is that the top quark can decay to a Z and a top quark. And so you just let that hypothesis be free, and you do different experiments that exclude different areas of this triangle. And what's plotted here are different hypotheses for the mass of the top partner. And as you see, there are like 5 different experiments here that exclude different regions of this triangle. And when you put them together, they're all excluded. So that particle is not at a mass of 800 GeV, or 900, or 1,000, or actually even 1,100 GeV. Some little phase space opens when you get to about 130 times the mass of the proton. So 1,300 times the mass of the proton. So that's a little discouraging, but maybe at higher mass, if we look harder, if we think of some other decay channel maybe that we hadn't thought of, that particle might appear. But so far it's a mystery. In this, again, very beautiful scenario that explains the Higgs boson and has a nice role of the top quark in that explanation, it predicts a particle that apparently doesn't exist. So maybe I should bring this talk to an end. There's one more topic, but let's skip through that. We do not know the role of the top quark in the broader picture of weak interactions. In the same way, we do not know why the Higgs boson has the property of filling space in an asymmetrical configuration. We know those particles exist. We know they have these properties. It's highly suggested in the way that I've explained in this talk that those two things fit together into a picture. But there are many elements of that picture that are still missing. And to discover those elements, we need to do new experiments with elementary particles, maybe different kinds of reactions, maybe at higher energy. The answers are out there, but we're still searching for them. So I hope that gives you a little picture of where we are today in elementary particle physics. And I hope you find these ideas interesting, and maybe some of you might like to pursue them. Well, thank you very much. Okay, questions? Yes?
Other than these possible models, do we have other things to increase the energy of the current experiments or for further experiments?
Well, maybe I should just say, first of all, there's nothing inexpensive about elementary particle physics. I mean, the cost of the LHC is something like $5 or $6 billion. It's a large facility. It's, as I said, a ring of 27 kilometers. The big question that we face now is, what can we do for a cost that society is willing to pay for? And it's a hard question, because if you think about building something bigger or more powerful, it would probably also be more expensive. So I think the whole community is grappling with that now. So one idea that people at CERN have is to build a tunnel, which would be a new tunnel 4 times the circumference of the LHC tunnel. And with that, you could go to energies 7 times the energy of the LHC, and then you can explore. But frankly, you can't like say, I will discover such and such a thing if I build this machine. You can only say, I hope to discover it. And the cost is something like $30 billion. So that's very scary. There's another strategy, which is a strategy that I talked about this morning in my lectures, which is to build a different kind of machine, an electron-positron, electron-anti-electron collider, that would look at the Higgs boson and study its properties with high precision. And that seems to be affordable, quote, affordable, in the sense that the cost is roughly the cost of the LHC. But then you still have to find a government that will give you $5 or $6 billion. And so that's discussions that are going on now. And then there are various machines that are proposed in these classes in different parts of the world. I'm very involved in advocacy for an accelerator in Japan that would do precision experiments on the Higgs boson. But, you know, unless there's a new accelerator, or unless the LHC, as it continues its run, will turn up some evidence for these particles, we're kind of at an impasse. I mean, we know there's something out there. We know there's a new mechanism that we have to discover, but we don't have clues as to what the nature of that mechanism is. And that's where we are now.
I was trying to ask if there are other motivations other than these things to build up the devices.
Well, certainly there's one more very important motivation, which has to do not with questions of elementary particle physics so much as questions of astronomy and cosmology. Because we also know, and this was the topic, no, I guess this will be the topic of a later public lecture in the series, that most of the matter in the universe is not contained within this standard model that I talked about. So we can look at the universe, we can see where matter is, and then we also see where stars are, and luminous matter, and clouds of gas. And it turns out that there is a large amount of matter. In fact, most of the matter in the universe is not in stars, gas, etc., but in some new kind of particle called dark matter. And dark matter is 85% of the mass in particles in the universe. And there is no natural place for it within this thing that I called the standard model. In supersymmetry, there are places for it. So maybe that's a motivation for believing in supersymmetry. In other kinds of these advanced models, you can find other places for dark matter. But there's no standard place. And maybe I should also say, in supersymmetry, the same exclusion that I talked about here also makes it somewhat less likely that you can make an explanation for dark matter. But nevertheless, you know, this is something that's very compelling to particle physicists, that 80% of the mass of the universe is not in our equations. And so another reason for building accelerators is to look for some production of those particles, and maybe if we can really create them in the lab, we can understand precisely what they are. So that's another important explanation. And then I think you can go on, but these two things are the really important things. What is dark matter? Where do quark and lepton masses come from? Why does the Higgs boson do what it does? It points to some bigger theory that we're trying to grasp, but we're not succeeding. And if we could grasp it, you know, who knows what's out there. Okay. Other questions? Yes?
My question about Suzy.
Yes?
Up to 10 TeV, there is not any signal of S particles.
Yes?
And upper limits excluded by naturalness of Higgs boson.
Okay.
What do you think about Suzy theories?
Well, you know, 10 years ago, I would have said when the LHC turned on, we will discover supersymmetric particles. In fact, I'll be totally honest. I said that, but it didn't happen. So I still think SUSY is very attractive, but you're absolutely right. It's now very strongly constrained, and the most attractive regions, the regions of its parameter space that were most attractive then, are excluded. I think there are other kinds of models, in fact, I indicated that in this talk, that are very much alive. We don't understand them as well as supersymmetry, but maybe that's a good thing, because there can still be surprises that would explain, for example, why the mass scale is so large compared to the mass scale of the Higgs boson. And so right now, I'm kind of ambivalent. Personally, my research is dedicated to these other kinds of models, but I still follow what's happening in the SUSY world. And I still hope that a supersymmetric particle will be discovered. Other questions? Please. Well, don't ask me. I've been wrong before. I don't know. I have an affinity for these models where the Higgs boson is composite. I think, as I say, there are a lot of aspects of those models that we're really ignorant about. But it means that it can hide surprises that can teach us something. So I'd really, what I'm trying to do in my own research is to see if we can learn some of those things which would be surprising. And so, it's a quest, it's not an answer. Okay. Okay, other people? Yes?
So I believe earlier today you described fundamental physics as peeling off, whenever you find something out, something new, you peel off a layer of ignorance and you ask another question about what's underlying
Yes.
this theory. So in what sense do these possible solutions stop this cycle of asking why and why?
Stop the cycle. Why do you,
When are we going to be, this may be a philosophical question.
Yeah.
How is it possible to be satisfied with finding a model that explains everything that we've been wondering about?
Well, I don't know. You discover something, you're happy for a week, then you find out that there are still questions, right? And I don't see any time in the foreseeable future that we're going to be satisfied. But remember, here we are at the scales of 100 GeV. We seem to understand everything. At the scales of 1,000 GeV, we understand much less. Probably at 5,000 GeV, we understand nothing. And the Planck scale is at 10 to the 19th GeV. So there's a long way to climb between here and there. And I think probably for centuries, people are going to be climbing that and discovering new things. We're just a little part of it. Sir.
Since this is your last lecture, in addition to reading your book, do you have any advice for young guys like us?
Well, as I've emphasized, both in the lectures and in this lecture, I think in order to make progress, you have to understand what happened before, right? If you do not know what the standard model predicts, then it's very hard to figure out when you see something, whether it's a discovery or whether it's just something that you already should have known. And I think it's very important when you're thinking about the really deep questions in nature to also learn about what we already understand and to use that as a foundation to jump forward. And so that's a theme I've emphasized in my lectures, and I think that's my big advice for you guys. And keep at it, because the mysteries, they're out there. We're going to find them eventually. Okay. Anyone else? Yes?
Sorry, since you mentioned the ranking of couplings in your slides, could you please talk a little about gravity also and compare, for example, the field, hypothetical field to the graviton or something.
Ah.
A huge difference between the value of that field.
Well, gravity, it's different. I mean, gravity does not couple with the dimensionless coupling. And so there's a scale, an energy scale at which gravity has similar strength to the other couplings. And that energy scale would be about 10 to the 18 GeV. So as I said, we have to climb very far up the ladder to get to the point where gravity has equivalent significance to the other fields in nature, viewed as the interaction of particles. Now, gravity has its own mysteries. Black holes, does quantum mechanics break down in the context of a black hole? I believe the answer is no, but it's a big question, and you can't just answer that question no, because there are big paradoxes associated with it that you have to understand, which I confess I don't understand. So the quantum theory of gravity is itself a very interesting study. But it doesn't have to do with elementary particle physics unless you think about energies of 10 to the 17 or 10 to the 18 GeV. I'm not discouraging you from thinking about that. I'm just pointing something out.
So at the time of Big Bang?
Well, at the time of the Big Bang, gravity might have been relevant. It depends what the temperature of the Big Bang was. Okay, we don't know that. It could have been a GeV. It could have been 10 to the 19 GeV. Anywhere in between, you can make a model of the Big Bang. I guess we're done. Let me take the rest of the questions privately. So thank you very much for your attendance.